Hi everyone, welcome to this algebra refresher. We're going to cover sections 1.1 and 1.2 from the textbook before the next class, where we're just going to jump into section 1.3. So watch this video before we get into that stuff. Let's start with the different kinds of numbers that we see. We'll start with the most basic and get to the most complicated. Let's start with the positive integers, also known as the natural numbers. We're going to typically favor the label positive integers, but there's nothing wrong with natural numbers. The positive integers is merely the set of all positive counting numbers, right? 1, 2, 3, 4, etc. All those positive numbers, right, that we can count. Now note that I put an ellipsis, ... because there is no end to the counting numbers, right? It goes off to infinity. Also just want to point out that these little braces right here denote a set, right? It's the set of elements, 1, 2, 3, etc. Okay? We're going to be using them a lot today. Maybe not quite so much during the semester, but you'll see them a little bit. All right, we next have the negative integers. You might be able to guess what those are, right? That's the negative version of this. All the way down to -1. It stops there. Note that the integers can be divided, really any set of numbers typically can be divided into 3 sets: positive, negative, and 0, which isn't positive or negative. So just keep that in mind. Right, so the integers is the negatives, the positives, and 0. And we typically denote the integers with the letter Z, with that extra line. And, we can just denote them as this, -3, etc., all the way from negative infinity, -3, -2, -1, 0, 1, 2, 3, etc., right? All the positive, negative, and 0 counting numbers. Integers are very, very fundamentally important. I want to highlight them because they're something you see a lot. Okay. Next up are the rational numbers, also very important. Rational numbers, denoted by Q for quotient, are the set of all numbers, well, I guess we could just say the set of all fractions A over B where A and B are integers. You know what, sorry, let me just for space concern, let me just say it's a set of all fractions A over B where A and B are integers. And we also have to include that B does not equal 0, right? Because we can't be dividing by 0. That's not allowed. Equivalently, you can say this is the set of all repeating decimals. Right? All decimals that eventually repeat are fractions. They can be written as fractions. Okay? Rationals. Another very, very important set of numbers. The irrationals. Also important, not so nice, I suppose. Right? This is the set of all non-repeating decimals. Not so nice. Very important, but not so nice. Next up, we have the real numbers. This is the most important set of numbers for this class, and for most math classes, maybe all math classes that you'll take. The real numbers is just the union of the rationals and the irrationals. Right? We denote the real numbers with R. And we say R is just all decimals. That's probably the nicest way to say it, right? Just all decimals, right? Repeating or non-repeating, okay? Then you also get into weird things like the imaginary numbers, right? That's the set of all real numbers times I, where I equals the square root of -1, right? Weird things happen when you take square roots of not nice numbers, right? If you take the square root of a number that's not a perfect square, then you get an irrational number. If you take the square root of a negative number, then you get an imaginary number. And then the complex numbers, denoted by C, is actually even bigger than the reals, because that's all numbers of the form a plus bi, where a and b are real, and I is the square root of -1. Okay? So that's all your numbers. We're going to focus on real numbers in this course. So if we ever take the square root of a negative number, we're going to say, hey, we're not allowed to do that. If we ever have a situation where there's a square root of a negative number, we say, nope, that doesn't exist, because we don't care about imaginary complex numbers. Real numbers. Okay? I just want to quickly go over a division. I'm hoping that this is mostly review, but it's very important to shore these things up. Property number 1, where we're coming up with this, these two fractions are equal, if that product is equal, well, what you can do is you just cross multiply, right? Multiply both sides by D, multiply both sides by B. Maybe I'll denote it like this. Right, and you can just see where we're getting our products. Okay. Number 2 is very important. Again, I'm sure most people know this, but the reason that number 2 works is because we have A over, here, actually, I can actually do it over here. Maybe I'll fit it in here. We have A over B times D over D. Right? On the one hand, that's AD over BD. But on the other hand, that's A over B times 1, which we know is just A over B. So that's why we get to do that. That's why the quotient is not affected by multiplying by D on the top and the bottom. We're just multiplying by 1. Number 3, just keep in mind, if there's one negative sign in a fraction, no matter where it is, top or bottom, that makes the fraction negative. Right? And of course, by the way, all of these have nice little illustrations over here. Okay. Number 4, fundamentally important law of addition, right? As we're going to see, addition usually does not work nicely with fractions. In order for addition to work nicely, you must have a common denominator. It doesn't work. You can't add two numbers otherwise. Right? Well, then the question becomes, how do you get a common denominator? Well, you use number 5, right? You have to multiply by the one denominator, multiply by the other denominator, and then you get the whole thing. Let me show you what I mean by this, right? So if you have A over B plus C over D, and you don't know anything about B and D, you have to assume they're completely different. You're going to multiply A over B by D over D, and multiply C over D by B over B. I'll move this over a little bit, right? This is going to give us AD plus BC, well actually, let me just do this separate, right? AD over BD plus, I'm going to reverse the B and the C and the B and the D, right? BC over BD, right? But notice that our denominators are the same. So now we get to use property 4 and add them together. AD plus BC all over BD. Right. So we used property 2 so that we could use property 4. Okay. So again, the thing to come away with is that fractions are not the best with addition, right? Because you have to do this common denominator stuff if your denominators don't match up. On the other hand, fractions work beautifully with multiplication and similarly with division, right? For multiplication, you just multiply straight through. Straight through. Now with division, just be a little careful, right? You're multiplying by the reciprocal. Okay, right? So make sure to flip that number over. In fact, let me maybe just note that we are flipping the fraction to get that. Okay? Please don't forget to flip it, but division is basically as easy as multiplication, right? And maybe that's not too surprising because fractions are division, they're quotients. So maybe it's somewhat intuitive that fractions work poorly with addition, but nicely with multiplication and division. Now, of course, you need to remember the addition and multiplication rules, but I think as a good guideline, just remember that you're in for a nice little ride. When you multiply, you just sort of go across the top, go across the bottom. Addition, a little bit more work. Now, let's take a look at example 1, right? How would you simplify a giant mess like this? Well, I'm going to go pretty quickly since we can pause the video, at any point, or go back and rewind. So, for starters, let me rewrite what we've got, because I think this is good writing, to write as much of a complete sentence as we can. Negative 2/5 plus y over z times 3/7. Now, just to be clear, simplifying, I'm going to simplify as much as I can. It'll look more simplified. I won't have any parentheses. I won't have any fractions on fractions. I won't have any unnecessary, multiplication symbols or anything like that. Let's see what we can do. First, what we're going to do is we're going to simplify the stuff in the parentheses. Okay? So what I'm going to do is I'm going to add w over x and y over z. I'm also going to divide by negative 2/5, and I'm going to multiply these two guys together. Okay? That's what I'm going to do. So let's see what we get, right? We're going to have a over b, and again, I'm not touching that right now. And then this is going to be times, let's see what we've got. W, so I notice I have w over x. I need to have the z in the denominator, right? So I have w over x times z over z plus y over z, but I need that x in the denominator, so I multiply by x over x. And now we're dividing all of this by negative 2/5, but maybe I'll instead multiply by 5 over negative 2. Right, because we know that that's coming, right? And now we can just do this other multiplication straight up, right? That's 3y over 7z. Always put your numbers before your letters. And get that, right? And just to be clear, right, here is your multiplication. Here is your fraction part, and then here is your division. Okay? So let's keep going at this point. We're going to get a over b times, I'm going to keep that extra parenthesis, wz plus xy all over xz times 5 over negative 2. And we can just keep this 3y over 7z going, right? Just keep that going, right? So at this point, looks pretty nice. Okay, a over b times, and now I'm just going to distribute the first two terms, like the 5 and the negative 2. So we're going to get 5wz plus 5xy all over negative 2xz. Now the problem here, in terms of how much work we've got, is that we've got another messy addition. Right? We're still adding this term to this term, and that's not ideal. However, do note that the denominators share a z. So when we're finding the common denominator, we need only multiply by 7 over 7 right here, and negative 2x over negative 2x there. Okay, so let's do that, right? So we get a over b times, and this is going to be 5, so I guess I won't use the parentheses for this since it's already a fraction. I guess we have 5wz plus 5xy all over negative 2xz times 7 over 7 plus 3y over 7z times negative 2x over negative 2x. All right, does everyone see that that's how we get what we want? I think we're running out of room here, so I'm going to cheat a little bit and maybe scoot this up a little bit. Okay, so then when we rewrite this and we simplify this, we're getting 35wz plus 35xy plus, or I guess I should say minus 6xy, right? Because I'm multiplying 3y and negative 2x all over this common denominator, negative 14xz, right? You see where I'm getting that from? That's this guy right there. So the last step is not that bad, right? We just multiply through by a and b, and we get 35awz plus 35 axy minus 6axy all over, well, a sec before I finish this, let's again move all this up. Try to move all of this up. There we go. And then we're going to have this all over negative 14bxz. Okay? And that is our final answer. Maybe I'll even separate that a little bit just so it's not so close. Okay? That's simplified, right? It's a reduced fraction. There are no parentheses. That's simplified, right? It took a little bit of work because of the addition. And I guess fractions on top of fractions, but even the division of 5 over negative 2 wasn't all that bad. It was the addition that screwed us up. So that's how you would do something like that. Okay, now I want to take a second to go over some stuff from section 1.2 where we get into sort of the next level of multiplication, right? Exponents and radicals. Just a quick little explanation for why some of these things are true. Property number 1, a to the m times a to the n, a to the n plus n. I will just say, actually, all of these things are things that my calculus students forget all the time. So it's very, very important to get this and to understand why. For example, let's just do an example, right? Remember that, first, generally speaking, that a to the m means a times itself, so that there are m copies of a, right? So for number 1, you've got 2 cubed times 2 to the 4th. Well, keep in mind that that's just 2 times 2 times 2 times 2 times 2 times 2 times 2, right? And then that's clearly 2 to the 3 plus 4. Okay. Maybe I should just say 2 to the 3 plus 4, right? All right, number 2. Again, something my calculus students forget this one all the time. They just have no idea what to do when you have a to the m raised to the n. Keep in mind, what is this really? Well, let's take a look. If we have 2 cubed to the 4th, well, that's the same thing as 2 cubed times 2 cubed times 2 cubed times 2 cubed. And then you can just add them all up, right? And I think it's pretty clear that that's 2 to the 3 times 4, right? Because you're adding 3 to itself 4 times. Number 3. Radicals work well with multiplication and division. Same with number 4, right? Radicals work well with multiplication and division. That's just how it works. Maybe that makes sense since we can define radicals through multiplication. Maybe that makes some amount of sense. But if you have, for example, right, 2 times 10 cubed, well, think about that. That's 2 times 10 times 2 times 10 times 2 times 10. And so I think it's obvious then that there are 3 copies of 2 and 3 copies of 10. Okay. Number 4 is very similar. Just remember, exponent splits the fraction. It's beautiful. All right, now number 5, I'm going to focus on A. B is just sort of a consequence of what we're about to discuss. For 5, right, just imagine this, right? You have a to the m over a to the n is going to equal a times itself, m number of times, divided by a times itself, n number of times. Well, supposing that, m is bigger, we're going to cross off some number of, I'm going to cross off n copies of a over here, all of them in the denominator, and we're just left with, some extras on top. So it makes sense that it's a minus, a to the m minus n. Again, if you just write out the fraction, that should be clear. One piece of notation that's very important that explains 5b is that a to the negative n is 1 over a to the n. 1 over a to the n. It's not actually a negative number. It's 1 over a to the n. Okay, so a over b to the negative n is b over a to the positive n, right? Because it's 1 over a to the b. And, of course, we should know that that's b to the n over a to the n. Last piece of notation, a to the 1 over n means the nth root of a. I don't have a preference which way you use it. I don't care if you use negative exponents or fractions, if you use fractional exponents or radicals. Just be consistent. Try not to use both at the same time. Try not to use both in the same expression if you can avoid it. Okay? And I encourage you to try to prove 1, 2, and 3 using the properties that we were just discussing up here. Try using it. It's pretty straightforward. And the hint is that, remember, the nth root, for example, of AB is AB to the 1 over n. Maybe I'll even just do the first one, actually, and I'll let you work out 2 and 3. Right, so remember, keep in mind that AB to the 1 over n equals a to the 1 over n, b to the 1 over n. Okay. By the way, it follows that a to the m over n can be thought of as a to the m to the 1 over n, or a to the 1 over n to the m. You can also think of this in terms of radicals, right? You can think of this as the nth root of a to the m, or the nth root of a to the m. Okay? Doesn't really matter. One last example that I assure you will not be as challenging or messy as example 1. We want to simplify this expression. Well, again, let's just rewrite it. 5th root of 3x to the 11th, that's the 11th, y to the 3rd, 9x squared, y to the negative 2. All right, we want to simplify this, so, try to avoid having x's and y's on both the top and the bottom if possible. Try to get rid of radicals when we can. Again, you can write this as radicals, or fractional exponents. I have no problem. I have no preference. But let's begin, right? So first of all, I'm going to work inside the radical, right? Leave the radical on the 5th root. Leave it alone. We know that 3 over 9 is 1/3. So, okay. We're going to be dividing by 3 at some point. We also know that we've got x to the 11th over x to the 2. So that's the same as x to the 11 minus 2, right, from the property that we were discussing before. y to the 3 over y to the negative 2, that's y to the 3 minus negative 2. And all of this is over only 3, right? That's not so bad. Let me drag this down a little bit just to separate it, okay? Okay, so that's great. We're going to reduce this, and we're going to get x to the 9th, the 5th root of x to the 9th, y to the 5th, right? Remember, minus a negative is adding, and then divided by 3. Okay? Remember, 3 over 9 is 1/3, so we're getting that. We've run out of room here, so what I'm going to do is draw a line and then continue my work over here. Let me just separate that as well. All right, anyway, at this point, notice that we can think of this fraction as the 5th root of x to the 9th times the 5th root of y to the 5th all over the 5th root of 3. Now, again, if that's out of nowhere, how did you get that? Well, remember, we could also write this as x to the 9th to the 1/5 times y to the 5th to the 1/5 all over 3 to the 1/5. And if you prefer. Oops, sorry, I should have written an equal sign right there. Always write your equal signs. All right, and then this will give us, you can keep it as x to the 9th, the 5th root of x to the 9th if you want. I'll just do it for right now. That's going to be pretty nice. 5th root of y to the 5th is just y. And then we can't really reduce the 5th root of 3. So we've got that. Now, if you want, you can also rewrite this. You can pull out a copy of x to the 5th, right? You can note that this is really the 5th root of x to the 5 plus 4. And so you can rewrite this as x times the 5th root of x to the 4th times y all over 5th root of 3. A little bit cramped down there, but that's what you can get, okay? So I just want to point out that this is a fine final answer. This is also a fine final answer. I have no preference with either, okay? Whatever you feel is more comfortable. I might do both. That's all we've got. Thanks for watching.